An unexpected visitor from another star system passing unannounced through the inner solar system is bound to ignite excitement, curiosity, and no small amount of speculation. And the object known as 3I/Atlas has done exactly that. As only the third confirmed interstellar object ever detected moving through our cosmic neighborhood, it naturally captured the imagination of scientists and the public alike. Whenever something so rare appears, especially something that did not originate around our sun, extraordinary ideas tend to follow. Among these ideas were claims that 3I/Atlas might be an artificial construct, perhaps even an alien probe sent from a distant civilization. However, as fascinating as such notions may be, careful scientific investigation tells a far more grounded and compelling story. A growing body of observational evidence shows that 3I/Atlas is not a technological artifact or spacecraft, but a natural interstellar comet shaped by the same physical processes that govern icy bodies throughout the galaxy. One of the strongest pieces of evidence comes directly from observations of the object's physical appearance. Astronomers using powerful telescopes, including the Gemini South Telescope through the NOIR Lab Educational Observing Program, have clearly detected both a coma and a tail surrounding 3I/Atlas. These features are not subtle or ambiguous. A coma is a diffuse cloud of gas and dust that forms around a comet's nucleus when it is heated by the sun, while the tail extends outward, pushed by solar radiation and the solar wind. These are classic, unmistakable signatures of cometary activity. Importantly, these features cannot be dismissed as observational artifacts, camera malfunctions, or visual illusions caused by data processing. Multiple independent observations, using different instruments and techniques, all confirm the same result. 3I/Atlas is actively releasing material into space. The presence of a coma and tail tells us something fundamental about the object's composition. Comets are rich in volatile materials such as water ice, carbon dioxide, carbon monoxide, and other frozen gases. When a comet travels from the cold outer regions of space into the warmer inner solar system, sunlight heats its surface. This heating causes the ices to sublimate, meaning they transition directly from a solid state into a gas without becoming liquid first. As these gases escape, they carry tiny dust particles with them, creating the glowing coma and the sweeping tail that we observe. This process is well understood and has been observed in countless comets originating from our own solar system. The fact that 3I/Atlas behaves in precisely the same way strongly supports the conclusion that it is a natural icy body, not an engineered object. Even a brief look at 3I/Atlas's tail is enough to distinguish it from an asteroid. Asteroids are typically rocky or metallic and lack significant amounts of volatile ice. As a result, they do not produce comas or tails when they approach the sun. While some asteroids can show minor dust activity under special circumstances, the sustained, well-developed coma and tail seen around 3I/Atlas are far more consistent with cometary physics. The object's visual behavior alone places it firmly in the category of comets, and there is nothing about its appearance that requires exotic explanations. Beyond how it looks, the way 3I/Atlas moves through space also reinforces its natural origin. Its trajectory follows a path entirely consistent with gravitational motion. Astronomers have carefully tracked its orbit and found no evidence of non-gravitational forces acting upon it. There are no signs of thrust, controlled maneuvers, or course corrections that might suggest propulsion or guidance. Instead, its motion can be explained simply by its initial velocity as it entered the solar system combined with the gravitational influence of the sun. This kind of predictable, passive motion is exactly what scientists expect from a natural object drifting through interstellar space. If 3I/Atlas were an artificial probe designed by an intelligent civilization, we would expect very different behavior. Such an object would likely be compact and unobscured, not hidden within a thick cloud of gas and dust. Engineers seeking to explore another star system would have little reason to surround their craft with volatile ices that obscure its structure and interfere with precise navigation. Moreover, an intelligent probe might be expected to alter its trajectory deliberately, perhaps approaching planets more closely to gather data or using gravitational assists in a purposeful way. 3I/Atlas does none of this. It does not dive toward Earth or any other planet, nor does it display any interest in specific targets. It simply passes through, reflecting sunlight as it goes, following the same physical rules as any other comet. Chemistry provides yet another powerful line of evidence. Spectroscopy, one of the most important tools in modern astronomy, allows scientists to determine the chemical composition of distant objects by analyzing the light they emit or reflect. Each molecule absorbs and emits light at specific wavelengths, creating a unique spectral fingerprint. By studying these fingerprints, astronomers can identify the gases present in a comet's coma and learn about its origins. Observations of 3I/Atlas using the Very Large Telescope have revealed the presence of molecules commonly found in comets from our own solar system. These include familiar volatile compounds that are known to form naturally in cold, dusty environments around young stars. While the exact chemical mixture in 3I/Atlas is not identical to that of comets native to our solar system, this is not surprising and does not suggest artificial construction. In fact, it is exactly what scientists would expect from an object that formed around a different star. Every star system has its own unique conditions, including variations in temperature, radiation, and the composition of the protoplanetary disk from which planets and smaller bodies form. These differences naturally lead to variations in the chemical makeup of comets. Rather than pointing to alien engineering, the chemistry of 3I/Atlas offers an exciting glimpse into the diversity of planetary systems beyond our own. The idea that an interstellar object might be an alien spacecraft is undoubtedly intriguing, and it reflects a deep human fascination with the possibility of extraterrestrial intelligence. However, science advances not by embracing the most sensational explanation, but by carefully weighing evidence and choosing the explanation that best fits all available data. In the case of 3I/Atlas, every major line of evidence, its appearance, its behavior, its motion, and its chemistry, points toward a simple, natural conclusion. It is a comet formed around another star, wandering through interstellar space for millions or even billions of years before briefly passing through our solar system. This conclusion does not make 3I/Atlas any less remarkable. On the contrary, its natural origin makes it scientifically priceless. Interstellar comets are messengers from distant star systems, carrying within them clues about how planets form elsewhere in the galaxy. By studying objects like 3I/Atlas, astronomers can compare the building blocks of other planetary systems with those of our own, helping us understand whether the processes that shaped Earth and its neighbors are common or rare. Each new interstellar visitor expands our knowledge of the galaxy and our place within it. In the end, 3I/Atlas reminds us that the universe does not need alien spacecraft to be extraordinary. The natural processes that create stars, planets, and comets are already capable of producing objects of immense beauty and scientific importance. While the search for extraterrestrial life and intelligence continues through many other avenues, this particular visitor appears to be a silent, icy traveler, shaped by physics and chemistry rather than intention. Its journey through our solar system is brief, but the insights it provides will last far longer, enriching our understanding of the cosmos and reminding us that even the simplest explanations can still inspire wonder.